Okay, good afternoon, guys. Today, we will start our last week about information retrieval with large language models. And I want to start with now we're ready to understand the DeepSeek models. So I want to start with this overview of this popular model now, DeepSeek. Uh, well, it's an example of paper with multiple authors. Um, so, what made people are interested in this model? So let's see if they have illustration. No, okay. So there are three main components that were kind of upgrade from standard language, previous language models. And the first, uh, let's see if I can find the illustration. Seek data ration. So the first important step was data preparation, because if we just use all the data from internet, then we can learn some garbage. And so the first step, mm, it's interesting, I can find. The first step was to use, they used a special pre-trained model that actually detected if this specific document is garbage or says something against communist parties. So we won't use this document in our training. And so it was the pre-processing. So they built and trained this model. And okay, I can find a good illustration. So, oh, but I can draw here. So, for large language models in general, there are following data sets: the internet, so all the data from internet, uh, some domain-specific data, maybe some documents, and a very important component, mathematical texts and proofs. So we use, of course, mathematics is also one of the domain data, but it's interesting. It was interesting observation that the model with which was trained also on the mathematical books will learn for tourism. And if we don't add this component, then it won't perform reasoning well. So it's an interesting observation that philosophy, which is considered by definition the science about the general um, principles of reasoning, is not useful for training language model, artificial intelligence. And I believe it's also not useful for human intelligence. But the mathematical component is really important for artificial intelligence, um, for to make the some reason-based conclusions. So they use these three domains. Then they use pre-trained model, which decided the processing. If the document is relevant or not. And was the first step. Then the other difference was in computational, what is called efficiency. So they proposed, they actually created the kernel for CUDAs that performed for a 8 bits multiplication on GPUs. You remember GPU works on 16 bits, and they also, so the second important kind of novelty in this LLM training was 8-bit matrix multiplications on GPU. So I think this is what actually people were interested in, because it's kind of hardware acceleration. And the third component is reinforcement learning with human feedback. We talked about this PPO algorithm last week. There is another algorithm proposed in 2023, DPO, direct preference or policy, maybe optimization. Let's look at the paper. And in DeepSeek, they modified this DPO algorithm. So so this is the kind of paper that they used in DeepSeek direct preference optimization. But you remember, it's still actually policy optimization if we call our model as policy. So if we use this model, which was proposed many years ago in reinforcement learning for ranking of the some events, which looks like softmax function. then we can calculate this sigmoid of the difference explicitly. And let's see. Aha. Yes, and then it will look as follows. The probability from large language model times this term, which depending on the higher or lower ranking, will make our large language model policy also output probability higher or lower. And if we substitute this in our formula, I hope it's you remember this formula from PPO, then um, it's the final formula. Yeah, so actually, yeah. Mhm. Aha. Okay, so as you remember, we should use the sigmoid of R, but R will be, if we derive this R from this formula 4, actually here it is, we will get the expression through our model, original language model, which wasn't fine-tuned, and the model which we want to fine-tune at 12 So this R reward will have the explicit expression through the like base model and the model that we want to find. And then the final formula. So this is actually sigmoid of R like winner minus R loser. But now the reward, we don't need to use the reward model. We can use just our model, fine-tuned model, that we want to fine-tune, and the not fine-tuned model. The idea is that we don't want to change much our original model because it works pretty good. We just want to modify it a little bit to return like some better to work better on some specific tasks where we actually used the labeling, the people who actually ranked the answers. Typically, it's done for specific, maybe for the specific company, then maybe the answers should follow the documentation of the company, or for to avoid what's called hateful lexic and so on. So this model is trained only on specific tasks, and if we change the weights of original model, then we can actually broke the model, and it only will always say thank you, and it will be not useful model. It will be polite, but not useful. So that's why we also add the so-called regularization, Kyle divergence. Let's see. Which will force our, it's here, KL divergence, which will force our new model to be close to the original model, not fine-tuned. So this was the idea of DPO paper, and in this DeepSeek paper, they proposed a modification of this DPO algorithm, which we called GRPO. So this is the third main component of this DeepSeek paper. So yeah, first the data preparation, second the hardware acceleration, and the third different loss function for RLHF. So if you look at this function, you should recognize PPO function, where it used clipping for the reward. So A stands for reward, and as you remember in reinforcement learning, we can subtract, which is called base model. So this is the average of rewards they use as the baseline, which reduces the variance in classical reinforced algorithm. And yes, instead of using the reward model, they use DPO, the direct preference optimization. And also they use mini batch. So they call this, that's why they call this group relative optimization. They use a batch of the texts, regularization term. So yeah, I think now you understand the main differences in this DeepSeek model architecture. So at least you can understand now what are the new approaches that were used in December last year. So these are just incremental improvements, kind of built, they built, but it's almost every paper, it just improves the previous results. So so no, there's no surprise that these improvements also will improve the large language model training. Okay, now let's talk about retrieval augmentation. Sorry, I didn't have time to prepare slides. So what are the large language models are good at and what they are not so good at? So what they're good at? Why do we use them every day?
Summarize things, generate new content.
So maybe to understand the context, large context. And what they're not good at, well, actually, it's what do you think? Which tasks they don't perform well? Yes.
I think they're really bad at saying they don't know. They make up an answer if they don't know one.
Okay, it can be fixed with reinforcement learning with human feedback. They can force the model maybe to say that most likely or something like that. But there are some examples here, like up-to-date knowledge, because they were trained on, well, actually currently ChatGPT goes into internet, so it can also capture like current information. But if we want to summarize a book, for example, like a, a thick book, even if using this rotary embeddings or alibi embeddings, you can use arbitrary length input to large language models, which is limited only by your hardware. But maybe it's not a good idea to tokenize a huge textbook and use this as a prompt. And maybe you want to learn to find information from multiple textbooks. Like last year, the one guy did a project, capstone project, where the model went to multiple economics textbooks in economics and built the portfolio based on, I don't remember, 100 or 500 companies, and it performed outperformed the some classical models for portfolio. So what if you want to do this search in many textbooks, then it won't fit also in the prompt. So this is another thing where we want to use retrieval augmentation generation. Yes, so these are examples. The idea of the retrieval augmented generation is very simple. It's based on k-nearest neighbors algorithm. So, if you remember, it was the first algorithm that we covered in machine learning class. The idea is to create the sentence embeddings. For example, you can use a textbook, split this into tokens of length 100, 200, just use arbitrary number, and apply kind of BERT model to get embedding of the sentences. And then we can create a database from these sentences and then apply also this model to the prompt and do the search between embedding of the prompt and embeddings stored in our database. And then based on the highest similarity, we can use top K, for example, embeddings, and by index find the original texts and use these small chunks of the texts as part of your prompt. So this is the general idea. But the problem is how to make it working fast, because k-nearest neighbors, as you remember, builds the distance matrix between all the vectors so if you have, for example, a million embeddings vectors, it will be a matrix million by million, and it won't fit any memory. So there are 10 years ago, there was proposed a graph-based search algorithm for k-nearest neighbors, and it is used in FAIS, the library for this fast search from Facebook. And this algorithm is called HNSW. So there is very efficient algorithm. Well, it's approximate algorithm. It won't find like all exactly top k vectors, but if it will find maybe 5 top in 10, maybe it's enough to for the large language model to generate reasonable answer. So the other algorithm, which also can be used to optimize this k-nearest neighbor search, is called inverted file index algorithm. So first, they split the vectors into clusters, and then they create embedding for the centroid of the cluster. And this also reduces the number of embeddings. And when then they find, for example, the closest vector, and then they apply k-nearest neighbor search only in the cluster which this vector represents. And here is the end of my slides. So, the first approach for this retrieval augmented generation was token-based. So let's talk about first token-based and then about sequence-based, which are used now. Token-based. So this is the paper generalization from memorization, nearest neighbor large models. So this was the first approach 5 years ago, 2020, which is not used in, but it's kind of the paper on the top of which other models were built. So let's say we have the what we want from the model. We want that model provides correct facts. For example, this is the question of Anna's birthday place. But there could be also another example. So they said, okay, let's find in our data set. At that time, data set was the Wikipedia data set that you can download from different places, even from Kaggle. It's pretty small and comparing with current data, which language models are trained on. And do the search in this Wikipedia for similar sentences, and then find in these similar sentences, for example, you can use entity recognition, the geographical names of the cities, and here are examples of different top K sentences from your training data. And then you can rank by the distance your this data and your request. Then you can calculate how many times one token was used in this nearest sentences. So here's the count, and then transform this with softmax into probabilities. And also combine here and gets finally the probabilities in your training set. And also you can calculate the probability with your large language model, because it also provides multiple probability for every token. So you can also calculate probabilities here, and then interpolate. Just take the well, it's not average because you can interpolate with some parameter lambda, so it's not just the average, but it's some number in between. And by the way, this lambda was trainable parameter at that point. So you can find the best lambda that interpolates these results, and the performance of model is better. And after this interpolation, you can choose the answer of the token. So it's very slow because you should do this for every token during generation, but it's the first idea. You will use the token kind of with additional information from your training data. The second paper about token-based generation is called Memorizing Transformers. And the idea in that paper was to use the previously generated context. So, and not from all layers of transformers, but from, I don't remember exactly, but from just several layers of the transformer. Instead of using the long input context as a prefix to our model, you can think about ChatGPT. You can use all the previous chat history as a prefix, but instead you can use just well, currently I believe they use chunks, but in this paper they propose to use just specific tokens, more relevant tokens from all previous conversation. Of course, it will reduce the input length in the transformer model. And so they stored, you remember in attention layer, we have 3 embeddings for every token, key, value, and what's the name for the third one? Key value and
Query.
And query, yes, thank you. And query. So they store only keys and values because queries are used from our prompt, and measure the similarity between it can be just dot product between all the stored tokens from previous conversations and our current prompt. Then they extract the most similar tokens and use them as inputs. So the attention mechanism will look at this small number of tokens from previous conversation. But again, it's token-based. The next paper, it's still token-based. They propose, instead of using the probability estimation for every new token, to keep track of the probability of like previously generated tokens, and then they built this kind of finite automata graph, where they also combined some similar tokens. And but again, you should build this graph for every prompt. For another prompt, you should generate a new graph. So it's also slow. Let's take a look at the sentence level generation. So now sentence level. And there was the first paper, Realm. You can see that it also, you can use it also from Hugging Face. A retrieval augmented LM. So at that time, they used simple models, BERT, and let's see, I don't remember, BART, maybe for generation. No, it looks like they used, or maybe GPT, I don't remember. Oh, T5. Okay. So sec-to-sec model. So the idea here was to create the embeddings for documents, for the entire documents in our data set. And when we have a prompt, we can calculate the probability of our prompt, and then retrieve the documents based on this formula 1. So this small probability document given prompt is calculated as just dot product between embeddings from BERT models. So it's kind of similarity. The first probability of the output given prompt and document is the generation from our large language model, but using as prompt also the document Z. And then they marginalize this with respect to documents, but of course in practice they use just mini batch, just several documents instead of all possible Z here. And then you can train. So this is your model actually that generates text. This is your model that generates embeddings. You can train 2 models at the same time. So this is the idea of the this paper, Real. Then the sequel of this paper is RAG, actually, the retrieval augmentation generation. So this is abbreviation, they used RAG here. The idea of this paper was pretty similar. Again, we have multiple documents in our data set. What was the difference? So again, we have two models, the retriever, which creates embeddings, and generator. In this paper, it was BART. So if I remember correctly, they didn't retrain the retriever, the model that created embeddings. They only trained the fine-tuned the generating model. Let's take a look at the loss function. But at least on the diagram, there is no trainable parameters for retriever. Okay, so next paper, improving language models by return from tokens. It's called retro, and their approach is pretty similar, but here they didn't train the retriever, but they used the data set of the say embeddings of your documents, and then they used in the prompt remember what this cow stand for, the different I don't remember how they use different similarity from different layers, or they use different chunks of the saved documents. But what they notice in this paper that you could use just pre-trained retriever without fine-tuning retriever, and also you could increase your data set with new information, and it improved the quality of generation. So this is a retro idea. And finally, the first architecture that didn't fine-tune the generator was called replug. Okay, so what do you think? Oh, we have just 3 minutes left. What do you think? Why the training on the retriever is better than training of the generator? So this model used the generator as a black box. I think the answer is very simple. Can you fine-tune ChatGPT? No, but you can use API and get the probabilities of the tokens. From other models, you can't get even probabilities, you can get only the generated text. So you can use powerful models, but you can't fine-tune them. The other thing is that typically generators are large models, very large, and retrievers less than 1 billion parameters models. So it's much easier to fine-tune the feature extractor model than generator. And here they used the models that return the probabilities, the logics from API. These are just 2 or 3 models that allow you to use the probabilities output, including GPT. And they try to fine-tune the retriever to align the retrieved documents probabilities with the probabilities, the outputs from the generator. And finally, the last paper, retrieval meets long context. In this paper, they didn't fine-tune neither generator nor retriever. So they used pre-trained models, and they said that if we just look at the previous context of our conversation dialogues and just take some most similar parts of the previous history with prompt and use this as input for generation, then it will improve the quality of generation, increase at least by 5%. So it means that you can use less powerful large language model, but if you add this retriever, then it will perform approximately as a large model. And this is what is used in practice. And next time we will talk about continue about talking this idea how to retrieve the information from your data or from internet. Okay, stop here.